Today we are diving into ammonia-based iron ore reduction cycle, a groundbreaking approach to sustainable iron production. This cycle consists of five key steps designed to significantly reduce greenhouse gas emissions. First, we have ammonia production, where ammonia is produced from renewable sources, making it a sustainable starting point. Next, in step 2 is ammonia decomposition. Here ammonia break down at high temperature. This decomposition leads to a step 3, which is release of hydrogen. As ammonia decomposes, hydrogen is released. The released hydrogen then drives step 4, that is iron ore reduction. Hydrogen reduces iron ore to metallic iron, completing the core reduction processes. Finally, we reach step 5, emission reduction. Through this entire cycle, greenhouse gas emissions are significantly reduced, highlighting its environmental benefits. Now coming to our next slide, which is about a ammonia consumption in iron ore processing. Understanding the practical application, let's look at ammonia consumption in iron ore processing. For every 1 ton of Fe2O3 iron ore, the theoretical ammonia consumption required is 213 kg of ammonia gas. These figures gives us a clear idea of the material input needed for this reduction method. Now coming to our next slide, which is focusing on iron oxide reduction and nitriding processes. Now let's break down the intricate iron oxide reduction and nitriding processes. This is not just about reduction, it is also involved the formation of nitrides. It begins with ammonia decomposition, where ammonia break down into hydrogen and nitrogen. Following this, we achieve reduction dominance. The iron oxides are efficiently reduced to metallic iron by the hydrogen. Crucially, nitriding formation occurs next. Here, nitrogen also releases from ammonia decomposition, reacts with iron to form iron nitrides. Lastly, we have nitride decomposition. These nitrides can then decompose back to metallic iron, demonstrating a dynamic and multifaceted process. As we can see on this slide, which shows the ammonia reduction rates. When comparing efficiency, ammonia reduction rate present an interesting picture. The initial reduction rate per minute for ammonia is 3.8 weight%. In contrast, for hydrogen, the initial reduction rate per minute is 3.0 weight%. This comparison indicates that ammonia can offer a faster initial reduction rate. Coming to our this slide, which focusing on enhancing iron ore reduction activity. So let's explore how we can enhance this process through a cycle that involves both direct and indirect reduction steps. Step 1 is direct reduction, where ammonia directly reduces Fe2O3 to Fe3O4, initiating the entire processes. Next, step 2 is catalytic decomposition. Here iron ore themselves catalyze the ammonia decomposition into hydrogen and nitrogen. This is a crucial step as it generates the reducing agent. Uh, This leads to a step 3, hydrogen generation, where hydrogen is generated. Finally, step 4 is indirect reduction. The generated hydrogen then reduces iron oxide species to metallic iron, sustaining high reduction rate. This integrated approach optimizes the reduction processes. Now coming to our subsequent this slide, which is focusing on comparative analysis of hydrogen and ammonia DRI in particular. When evaluating different direct reduction iron methods, it's essential to conduct a comparative analysis of hydrogen and ammonia DRI. We consider several critical factors: reduction mechanism, the specific methods used to reduce iron ore. Let us see about the kinetics, the speed and the study of the reaction involved. Byproduct, let us see what other byproducts are formed during the reduction. As for energy efficiency is concerned, here it also shows that how effectively energy is used and saved. And in the similar way, infrastructure and supply, the logistic and the challenges related to supply chain has been also shown. As for the material impact is concerned, the effect on the properties of iron is also shown. In environmental impact has been also highlighted, the carbon footprint and overall sustainability. As for the temperature range is concerned, the optimal operating temperature for the processes has been compared. The thermal effects is also given in the to compare, and this is about thermal effect is about how heat is managed and its efficiency. Now coming to our next slide, which is about the iron production processes. Visualizing the stages, the iron production processes involve a sequence of transformation. Similar to a plant growing from a seeding, the process evolves through different stages. It begins with direct reduction, followed by ammonia decomposition, then progresses to hydrogen reduction and can culminate in iron nitride formation. Each stage, each stage contribute to the overall production of iron. Now coming to the comparison chart in this slide, where ammonia versus hydrogen reduction has been compared, and let's directly compare ammonia versus hydrogen reduction by looking at their pros and cons. For ammonia based direct reduction, that is ADR, the pros includes similar. As for the kinetics, both ammonia and hydrogen methods efficiently reduce iron ore to metallic iron at 700 degrees centigrade. Energy, as for energy saving is concerned, ADR saves 18% energy by avoiding ammonia cracking, which is a significant efficiency gain. Established infrastructure regarding these, ammonia benefits from existing global supply chain and logistic, making it very easier to implement in any upcoming project. Let us also see about the Bennigan byproducts. ADR produces nitrogen as a Bennigan byproduct and iron nitrides, which offer corrosion protection benefits. As for thermal efficiency is concerned, nitrogen enhances thermal management in shaft furnaces, improving overall process efficiency. However, oxygen based hydrogen based direct reduction, that is HYDR, has its some cons also, like a water byproduct. HYDR produces water vapor which require additional handling. No nitride formation in HYDR doesn't form iron nitrides, meaning it misses out on corrosion protection benefit that nitride offer. High initial cost as for HYDR requires significant investment in hydrogen production and specialized storage infrastructure, leading to higher upfront expenses. And now coming to the our very conclusive slides, which is on choosing the most efficient and cost effective direct reduction method for steel production. And finally, when we need to choose the most efficient and cost effective direct reduction method for steel production, the comparison becomes clear. On one side, we have a ammonia-based direct reduction (ADR). It offers cost saving and easier handling, primarily due to its established infrastructure and many gun byproducts. On the other, hydrogen-based direct reduction, while viable, it requires hydrogen production and specialized storage, leading to higher infrastructure cost and complexity. Based on these factors, ammonia presents a compelling case for efficiency and cost effectiveness,